Assalamu alaikum. Hi.
Walaikum salam.
Walaikum. How are you? Good?
Fine, fine. You
Fine.
teacher.
Alhamdulillah. Summa alhamdulillah. Summa
Alhamdulillah.
alhamdulillah. So I hope now we have uh, six, 16 minutes. So we can start now. So Bismillah ar-Rahman ar-Rahim. We are going to start equipment design course. Um, this is a course plan here in front of you. As usual, we will start with some introduction. Then we talk about how to get the design data. As you know, the course topic is equipment design. This course topic, equipment design. So you are supposed to design the equipment, right? So before you design, you need to have a data available. Okay. So today we talk about how to get data. Okay. Then we talk about design of the flash drum, and then we talk about storage tanks. Then we talk about cooling towers. All they are used in industry. Then we talk about compressors, talk about pumps, heat exchangers, distillation towers, absorption towers, and in the end is pressure vessels. So here you will find more difficult heat exchangers and distillation tower. These two are difficult, okay? But rest of them like flash drum very easy, storage tank very easy, cooling tower yeah they somewhat difficult. Compressor are okay, pumps are okay. They are very not very difficult. Okay. So inshallah, when you finish this course, you will know how to design any process equipment. Now this design is more of a mechanical point of view plus some chemical point of view because we are talking about here the sizing of the equipment. Like what is do you mean by the designing? Designing means the size you have to calculate the how big should be the pump or compressor, like the size of the equipment, and you also have to know the shape of the equipment. Should it be cylindrical or should it be spherical? That you have to calculate, and you have to decide what is the best for your plant. So overall objective of this course is that when you take this course, you should be able to design various chemical equipment. And this design is not detailed. Only we talk about very basic because designing is not an easy job. You need to have a software like Aspen and other softwares. Okay. So we talk about very basic designing. We give you the foundation. Okay. And then you can go ahead and you can do your search. And when you do the senior design project, this course is very important for you because in the senior design project, you will be asked to design the process plant and the equipment. Okay. So this course is very important. You have to understand. Okay. So this is about this course. Now for the book, let me share with you the book. 1 minute. Chemical. Okay. Here are the books. You can see there are a lot of books available to design the chemical process equipment. Okay. You can use as a reference book. Like yeah, this is very easy. Chemical process equipment. Okay. You can use this one as a reference. Our textbook is This one by Govin, this book, Govin and Towler. This one. Yeah, Sinod and Towler. Chemical Engineering Design. This will be our textbook, and I will be covering a lot from this book, Chemical Engineering Design. But if you have problem, you can either ask me questions or you can use uh, many of these books. You can download. They are available uh, from any site. So these are the reference books. Okay, these are the reference books. You have any question?
Clear,
माफी सवाल? Okay,
clear,
जरा
clear.
Clear.
शुक्रान शुक्रान. So now we start with our. I have already uploaded the lecture number 1, where we are going to know how to get data. Okay, so let me go back and share. Mm, uh, okay, 1 minute. Share. Application window. Application window. This is module 1. I already uploaded uh, in the system. You can download. And in this today, I will just tell you how to get the data for the designing data. Like, what do I mean by data? I mean by data is like the viscosity. Because if you are designing a pump, you have to know the viscosity, Lazuja, of the fluid and the density and thermal conductivity. This all we need. Okay. So anyway, now we start. Should be DSIGN. Design. Okay. See, what is the objective of a chemical engineer? The objective of a chemical engineering job is that you make a useful product. Like from crude oil, we make very useful product like gasoline. We manufacture diesel oil, furnace oil, LPG. They are useful product. Crude oil is not a useful product. Okay, so we convert. So this is a job of a chemical engineer to make useful product from the raw materials. Like you make a soap or you make a cement, you make glass from the raw material. So when you do this, you need something, right? You need some equipment. So basically, your job is to do the selection, right? To select the best equipment after designing, and then you have to operate it. All these three are the responsibilities of a chemical engineer, as well as maintenance. It's just like you buy a car, you choose the best car for your purpose, like it may be Camry, it may be Hyundai, Civic, whatever. Then you select according to the design, comfortable, not comfortable, having, Sasha, having Wi-Fi, whatever. And then you operate and maintain your car. Similarly, you operate and maintain your equipment, such as pumps and compressors and heat exchangers and pipes and valves and separators. These are like your babies, like they make you money. So you have to be very careful when you operate them. So operation and maintenance, you have to be very good in it. Designing comes on a very advanced level. Designing when you are very experienced, when you go and join the Aramco or you join the Sabic, they will not give you designing. They will ask you just to learn the operation of the plant, operation and maintenance of the plant. When you become very experienced in operation maintenance, then they will give you the job of selection and design. That's how they do. You will not go directly to design. Okay, but you should have some basic knowledge of designing, so that when you operate and you maintain, you will know what problems can be. You can face problems when you operate and operate and maintain. Okay. So in this course, we will focus on design techniques of major chemical process equipment and selection. See, definitely we cannot cover all the equipment in industry. We only cover major equipment and it will clear your lot of your concepts. Okay. For example, this is our plant. So, for example, somebody comes to you and he says that I have like 1 billion real. I want to establish, I want to make a plant, ammonia plant. I want to manufacture ammonia. Why? Because there is a demand of ammonia in Saudi Arabia. So now you are a chemical engineer. You start thinking, okay, how can I make ammonia from nitrogen and hydrogen? Okay, so you say, okay, I get nitrogen from air. Okay, I separate nitrogen from oxygen in air, and I can get hydrogen from natural gas. Because natural gas, when you decompose natural gas, which is methane, you get hydrogen and ethylene. So you mix 1:3 ratio by this stoichiometric ratio 1:3, like 1 mole of nitrogen, 3 mole of hydrogen. You mix it here, and then you give it to the reactor. So this is the temperature of the reactor, 400 to 450, very high temperature, and the pressure is also very high, 200 atmosphere, and you need an iron catalyst. The reaction occur here, this reaction, it goes on here inside the reactor, then the product leave. And these are composed of ammonia and not always complete ammonia. You will also have some hydrogen and some nitrogen. So you separate, this is a separator, you separate ammonia and you recycle back hydrogen and nitrogen. Here, you recycle back this way. Okay. Now this is your equipment. Now you have made a block diagram. The first step that you make is to make the block diagram, right? Now you look at what are the conditions. This is the most important part of your plant, the reactor. Okay. In the reactor, you see the temperature is very high. It means what? It means that you need a furnace, right? That's how you get. You need a furnace to heat nitrogen and hydrogen. So we need a furnace. You tell your boss we need a furnace because the temperature is very high. Then the pressure is also very high. So you need to tell your mudir that we also need a compressor, right? Because it's very high and these are gases, not the pump, right? They are gases. So you need a compressor. Then you say that we also need to buy a iron catalyst. So here I can see now, because the reaction is not complete, we need a separator because we cannot put hydrogen with ammonia and nitrogen will destroy ammonia. Usually your customer, he wants pure ammonia. He doesn't want any nitrogen or hydrogen inside ammonia. Okay, so or any kind of water, something, sometimes water also comes. So you need a separator so that you can separate ammonia from these reactants. This one. Okay, so how many equipment we need? We need two compressors to compress this. We need a mixer here, mixer. Then we need a furnace, and we need a compressor. We need a reactor to put the iron catalyst. Then we need a separator. This is known as a block diagram. First step. Okay. Then you go for process flow diagram. This is process flow now. This you will see in 401 when next semester. This is taken from Aspen. And now here, this is a mixture of 1/3 ammonia. Okay, this is we need a compressor because as I told you, we need a very high pressure. This ammonia and this is a recycle stream, recycle. So after we need a mixer because we have a recycle here, as you can see here. Uh, we need a recycle here, so we need a mixer here, mixing, right? So we need a mixer here. Here, this is a mixer. So you need a compressor because you have high pressure in the system, and you need a mixer because you want to recycle it. Then you need a heater because the temperature is very high. And if you do not need high temperature, you don't need this equipment, no need. Okay. Then you have a reactor here. Okay. Then the cool down because the temperature is very high after the reaction, you cannot store. You need to cool down the system. Then here you come, a separator. Here you separate the liquid ammonia, and here nitrogen and hydrogen they are recycled back. Some charge is removed because of the impurities. Whenever you have impurities, you must remove impurities from the system, like inert gases. Okay, and you recycle back. So this is now your complete plant. Once you make the process flow diagram like this, now you start thinking, what should be the size of my compressor? What should be the type of my compressor? Should it be a positive displacement or should it be a centrifugal? The type and the size. Okay. Then you come here, you have to decide about what type of mixer you need. Should it be a valve or should it be a mixer? Then you come here. Do I need a heat exchanger here or do I need a furnace here? You have to decide here. Then you come here. You have to decide about the reactor. Okay. In this course, we will not talk about the reactor design because this is a part of reaction engineering. Other than reactor, we talk about something. Here, then you cool down. Here, you have to decide what type of heat exchanger should I use here. Should it be shell and tube and what? Then you come here. You need to calculate, design the size of the flash drum here. This is a flash drum here. And then you come and decide here how can I separate the impurities from the recycled stream, and that's how you design. This is another compressor because here pressure is low. Okay, the pressure goes down as we process through the reactor. So you have to boost up you have to increase the pressure because otherwise this is high pressure and this is low pressure. You cannot put the low pressure steam into high pressure steam because it will go back this way. We don't want to this high pressure to go here. No, we want both pressures at least should be equal. So here you need a compressor. Okay. So equipment design you have to focus on the type of the equipment, the type, which type INO, and the size IMACAS, the size and the type of the equipment. Okay.
I'm sorry, doctor. You mean in the process flow diagram, uh, part of it is the sizing and the types, or
Yeah, yeah, the
it's a,
size. What
ah,
I'm saying that in design, you have to decide upon the size of the equipment and the type of the equipment.
okay.
Okay, now is it clear so far?
Yes,
No
clear.
question.
Yes.
Okay, this is just an introduction because if you know why you are taking this course, you will be more interested. Otherwise, if you have no idea, so this I'm just giving you the background. Today only I will talk about the background today. So again, compressor used but in high pressure, heater is used but in high temperature, reactor is carry out conversion, cooler is used, cool down the product, separator is used to separate the product. Okay, now these equipment are very expensive because Saudi Arabia is not manufacturing. Saudi Arabia import this equipment from Europe and America, and I think maybe Russia, Romania. Romania is very well known. Romania. So these equipment are imported. When the equipment are imported, they are very expensive. Okay, they are not manufactured locally. Saudi Arabia does not make equipment locally. You have to purchase from outside. Okay. That is why you have to be very careful as a chemical engineer to make the right design. If you oversize this, like compressor oversize, you have to pay more. That will be the loss to the company. Okay, this is very important that you design very accurate because it's a billion dollars, $1 million or maybe billion real are required to build up a complete plant here. Okay. So even you make a slight mistake, the company will suffer a huge amount. You guys have to be very accurate in designing and selecting the equipment, the right equipment. Okay. So point number 9 in designing, we consider the size, the shape. These are two basic that you will learn here. Ease of operation, how easily you can operate. If you buy something that you cannot easily operate, then it is useless. If you buy something that is not safe, okay, it is maybe less price, more economical, but not safe, useless. It should be it should be corrosion resistance, right? And it should be very powerful, structural rigidity. So these things you have to consider. But in this course, we only talk about how to calculate the size of the equipment. Shape, I can also discuss some shape, but these two will be the basic thing. Because ease of operation and this, there are no calculation involved here. You can read the literature or you can go to your company when inshallah when you find a job there. They have a lot of manuals available, operating manuals. So and safety, safety is also you can find a line. There is no calculation involved in safety. And corrosion, if you take the test on there is a course in our department. corrosion. There you can learn more about corrosion. Okay. So here in this course, we only talk about the size and shape. Okay. So how to design the equipment? The first step in designing an equipment is to know the physical and chemical thermodynamic properties of the fluid passing through it. Because as you see, the fluid is, I mean, ammonia, hydrogen, nitrogen. They are different fluid and they have different properties. They have a different densities. They have different thermal conductivities, right? And that is why the equipment processing equipment are different in size and shape because the properties of the fluid. So it is very important that you know the right chemical and physical properties. Yeah, the right to know the right physical to know the right or accurate physical and chemical or thermodynamic properties and thermodynamic properties. These are minor changes. Don't worry about it. Okay. Okay. These properties are density, viscosity, conductivity, vapor pressure, rate constant for the reaction, and the diffusion constant when you are having distillation. In distillation, diffusivity is very important, and the mixing processes. So how do we get these physical and chemical properties? They are listed in the handbook. If you go, there is a well-known handbook, chemical. I think Paris Chemical Engineers Handbook. Paris Chemical Engineer Handbook or monograph data. These are the data tables. Okay, the chart. These are the charts. Graph always means charts. Okay, table or from correlation. Suppose you go look into the handbook, you don't find it. You look for the monograph, you don't find it. You look for the table, you do not find it. Correlation, you they have no idea, you don't get it. So the last thing is that you have to do experiments in your lab, in your Aramco lab or your Sabic lab or in your I don't know another maybe Marafic lab. You have to do the experiment to get the data. If you cannot find the data, you need to do experiment. Okay. So some sources are available. So first of all, see, your job as engineer is to save money for the company, right? So you will always go for the free resources. Free resources. So these are some free resources available. These are known as, you can try it. Yeah. Oh, 1 minute. Freely available resources. So here we have, why this is 1 minute, 1 minute, 1 minute. This is, if you type this, National Institute of Standard and Technology database. Okay, so you can find here free. This is available free to all, but you will not find most of the data here. So because this is free, of course, so maybe sometime you will not find what you are looking for. Then if you want to look for the chemistry data, you can type this in the Google. You can get it. Then they have this chemical kinetic database. You can also get it. Then ionic liquid database. Like this is a special case. You will not be dealing with this one, but I just include as an example. What are ionic liquid? Ionic liquid are complex structure salts that behave as liquid below 100 degree or even at room temperature. Okay, this is just a definition of ionic liquid. Don't worry about it too much. These are different types. These are the ionic liquid definition, and these are their uses. Okay, ionic liquids. So here we have these are the structure of ionic liquid. So don't worry about this one. Just an example. Okay. Then another source that you can get data from is called MetWeb. You can search it here, metweb.com. Okay. Another source that you can get is ChemSpider. You can get it here also. So here, if you are interested in the chemical structure of a compound, you can get from ChemSpider. Another one is MID Plus, and another is Mark Index. Another is Novel. Okay. Now, when you do not find your data here in the free resources, then you look for the paid resources. Paid. And the paid resources are many. You have to pay there, okay? You have to use your credit card or your debit card. These are the CRC Handbook of Chemistry, ChemNet Base, ChemNetBase.com, Landauer, Bronstein, Rexel, Graham Handbook, Chemical Effect, Inspect, Compendex, Publisher website, Google. Google Scholar you can find. Same link, same link. Okay. You can try this one. Show me next time. No, right now we don't have time. Find the properties of carbon dioxide by using all the site databases. Like you can go to the NIST, go for the free, find the properties. Like property, I mean, as I told you before, at some temperature, find the density, viscosity of carbon dioxide, density of carbon dioxide, and the thermal conductivity of carbon dioxide. Okay. Now, now you have the resources, right? These are all the resources from where you can get data. This one. Okay. Then another question come into mind about the accuracy. As I told you before, you have to be very accurate in designing, and the designing depends on the data accuracy of data. If the data is accurate, the design is accurate. If data there is a problem with data, the design is wrong. Okay, so the data should be reliable, that you can rely on the reliable source. The source it should be validated against the experiments, and it should be according to the condition of the equipment. For example, you are running the reactor at 400 degrees centigrade. So the data, the rate should be at 400 degree. You should not use it other than 400 degree data. Okay, you cannot put data which was at 300 degrees centigrade, but that is wrong, right? So, second thing, the part B, there should be no inconsistency in the data. What does it mean? It means that the data should make sense to you. For example, as we know, when we increase the temperature, the pressure increases with temperature of a gas, right? But if you see in the data that we are increasing the temperature, the pressure increases and then it goes down and then increases. So this is called inconsistency. As we know that pressure will not decrease when we increase the temperature, right? So sometimes you see that data show abnormal behavior. This is called abnormal behavior. Where adi. So you have to look when you get the data, it should not have any inconsistency. You will all learn it when you join Sabit, the design department, they will all tell you about this. In fact, they have a lot of courses on how to get data. It's a separate subject altogether. It's called data analysis. Okay, data analysis is a very important subject and it's very long. I just gave you basic information about it. Okay. So how do you know the data quality? The data should have no inconsistency. This one, it should be complete and it should be accurate. So how do I know accuracy? Accuracy is the real value divided by the measure value. Now let me give you an example. Suppose you want to measure temperature of in Yambu. Okay. So we use 5 different thermometers, right? 5 different thermometers we are using to measure the temperature of Yambu. Here, 5 different thermometers we use to measure the temperature of Yambu. So let's say the first thermometer gave us 36 degrees, the second thermometer 36, because they're all different manufactured from different companies. Okay, the third one gave us 35.5, the fourth one gave us 36.2, the last one gave us 35.9 degrees centigrade. So what we do when you get this, when you collect the data here, you take the average value. The average value is 36.02. Now we see how much this temperature is away from the average value, 0.02. How much this temperature away from the average value, 0.48. This also 1.48 like this. So we see the deviation, the fark. So we take the deviation from the average value and the real value. The difference between the real this value and the average value. This is called deviation. Okay, in half maybe. So here we can take the so this would be zero point 0.2. It should be 0.02. I made it mistake. It should be 0.02 because this is okay here. Then 0.48, 0.52, 0.18, and these are the deviations from the average value. Now we take the average of the deviation, like we sum these together, we sum these together and take the average. So this is the average. So you report accuracy by this. As you can see, this is the average value of the temperature, and this is the average value of the deviation. So you write whenever you see many points when you work in a company, they report data like 36.02 degree plus minus zero point 0.3. So this range is like plus means 36.32, okay, and minus means 35 points. So this is a range. So this you say this is the acceptable range, okay. So you establish. So this is you establish, okay. Now you use the sixth thermometer, the system, and it reads that it is because I want to know how accurate this thermometer is, the sixth thermometer, okay. So what I do, I measure the temperature from this thermometer, and I would like to know how accurate is the thermometer, okay. And another thermometer I take, seventh thermometer, and it is 36.7 degree. So as I can see, because the range is 36.32 to 35.68, and this is 36.7, so this is out of the range. So I will say this is not very accurate, okay. But this is acceptable. The accuracy of this thermometer is acceptable, and accuracy of this thermometer is not acceptable because this temperature is out of the range. This is the range. This is acceptable range. This one, okay. You have any question here?
So you mean, doctor, by the average of the deviation, we can know the range of the good.
Yes, yes, very good.
Okay.
Yes, yes, yes,
Yes.
very good. Just a simple example. I hope everybody understand. Okay, now move on to precision. So this is how you determine the accuracy. Okay, they do a lot of tests. I just show you 5 tests for simple example, but they do thousands and thousands of tests, and then they establish the range. Then they establish the range. Okay, this range. Thousand they do thousand, not 4 or 5 thousands. And then when you come up with a new thermometer, you can see how accurate is the thermometer based on this range. Based on the range here. Okay. Now what is the precision? The precision, now we are talking about data here, okay? Don't forget that we are talking about data. Now, what is precision is? As engineer, you should know where, because you are, first of all, you know the source of data from where you are getting. Secondly, you have to know the reliability of data. To check the reliability, you have to know the accuracy, how to know the accuracy, and then how to know the precision. Okay. Now, precision is defined as the closeness between the measured values. Now, you have a thermometer and you start measuring the temperature, and you say, okay, 36.3, 36.1, 36.5. We would say he's very, the engineer is very precise. Sorry, the thermometer. I should not write he here. It is very precise because the values are close to the established value of 36.02. This is our established value, and all the values we measure using one thermometer, they are close to the established value. It means that the thermometer is very precise. Got my point?
Yes.
Precision means all the values that you measure, they are very close to each other. When the values are close to each other, you say the precision is high. When the values are close to the real value, you say it is accurate. Accuracy, accuracy when the measured values are close to the real value. Okay. Precision. Precision when the measured values are close to each other. When they are close to each other, not to the real value. Maybe they are far from the real value, but if they are close to each other, it means they are precise. Okay, this you can note down now. So this is one way. Okay. This is one way getting data from the handbook, from the literature, from the search. Now suppose you do not find the data from the handbook or whatever, then the second option is, this is the second option, that you use equations, mathematical equations, to calculate the data. Okay. So now, for example, this is a flat drum. 1 minute. Where are we? Okay. Yeah. This is our drum. So as you can see in the drum, we have a mixture of vapor and liquid coming inside. So the liquid is going down and the vapor are going up. So here we would like to know what is the vapor pressure, the pressure of the vapor, because the pressure vapor tells you about the size of the separation of the component and the size of the drum. So here we have to know the pressure. What is the pressure? What is the vapor pressure here? So we need to calculate, right? We need to calculate what is the vapor pressure here. Suppose you do not find in the handbook, then you can use this equation. This equation is used to calculate the vapor pressure at a given temperature. For example, if I want to calculate this compound, NDCane, the vapor pressure of NDCane at 30 degrees centigrade, 30 degrees. So I will put the temperature in 30, not as Kelvin, okay, as in centigrade here. And I put this constant like A, here I put 6.954, here B I will put here on the top 1497, and here C I will put 197 here. So when I put all the data, I can calculate in log the pressure, the vapor pressure in millimeter Hg. Okay, so for one way is that you get data from the handbook, from the monographs, from the table. You look at their accuracy, you look at their precision, or and then if you cannot find data from the handbook, then the other option is that you go for the equations. Okay, so these are the equations. So this is just an example how to calculate the vapor pressure of the compound. So this know in thermodynamics, used very well in thermo. This is a thermodynamic equation. Inshallah, we will see it when I cover, I think maybe after the midterm, maybe major two, when we study thermodynamics, when we talk about the separation process in thermodynamics, you will see this equation for the vapor pressure. Because we cannot have data available at any point, so we can use the equation in the handbook. Okay. For the water, you have to use this constant for the water. And remember that the unit are SI unit. That is why they write very clearly. The unit, you must use mmHg. You must use centigrade. You cannot use here Kelvin. Otherwise, the value have to be different for A, B, C. Okay. You must use Kelvin. You cannot use Kelvin or Rankine or Fahrenheit. You can only use here centigrade. And that is why they write in bracket to be very clear about this in mmHg. Okay, very clear. That is why some equation you will see the units. If I give you in PSI, you convert to mmHg. Lazim, like very important that you must convert to mmHg. Must convert to centigrade, and then you put here. This type of equation is known as a correlation. Well, now what is correlation? See, correlation is something that you obtain from the experiments. You cannot explain the behavior. I cannot explain why this equation is A minus B over T plus C. There is no logical explanation. Okay, there is no theoretical explanation. It's just we got from experimental data. We fit the data. We got data. And we got the temperature and the pressure. We have a table of temperature and pressure. Okay, and from that we put into Excel, and the Excel gave us this equation. So this is just called as correlation. Correlations will not tell you why this is log and why this is A minus B over why this is kind of. You cannot do like this. This is just a correlation. The form of the equation you cannot explain logically, because just from the fitting of the equation. Okay. Now this is fitting of the equation. Sometimes you can use the law as well. Now law you can explain. Like for example, the Boyle's law, the Charles law, the Dartel law, partial pressure. Ideal gas law you are familiar. PV is equal to nRT. Here also you can get the data. Why, like for example, if I give you pressure and temperature, you can calculate volume, right? So this is by the law. This is by the you can explain this, but correlation you cannot explain. You will see in thermodynamics more. This is just an example here. Okay. Okay. Let's have a break now, and I think we come back 2:15. All right.
215,
Okay.
doctor?
Yeah, yeah, 215. Okay.
Yes, yes.
Okay.
All right. Masalam. it is there automatic. Whether you come and go, what time you are coming, what when are you leaving, this is all recorded here. Okay, so this is the thing. So I will not ask you again to put your ID number in the chat box. No need. It's all automatic now. Okay. So now we were talking about the equipment design, and we were talking about how to get data. So I told you I told you about two options. One is that you find from the handbook, monograph tables directly. You don't have to do any calculation. Just go and read. Sometimes you do not find data from the handbook, so you need to use the equations. And I gave you example of entire equations, and I gave you entire equation as an example of a correlation. Okay, why this equation has this form? Okay, we cannot explain. It's just from the data, behavior of data. Second, I told you about how to get data by using the laws. Now laws you can explain because this is you see by your own eyes that when you increase the temperature, the pressure also increases. So this is you explain, right? That's why we had this form because when you increase the temperature, the pressure will increase. So they are proportional. So this you can explain, but explaining this equation above is not possible. Why this why this form of equation? Uh, very good. Yeah, why this form? It's not possible to explain because this is just a correlation. So anything you cannot explain, get from the data fitting, you call it a correlation. This is not law. But when you develop a law, you call it that Boyle's law, like for example, according to the observation. This is observation. Yeah, here you can observe. Okay. So now, if you look for data, you can also use the ideal gas equation, for example. As you know, density is mass upon volume. So I can write this equation as if I go mass upon volume. So I will write P here. P is equal to N over V, right? V is go other way, RT, right? So this N over V is known as a molar density. This one, molar density N over V, right? Because this is not mass, this is mole. N. So this is molar density. So I can write P is equal to density. Uh, let's say I call D as a density into R into temperature, right? So for ideal gas, if you want to know the density at any temperature, you can use ideal gas law. Yeah. But if you have a real gas, not an ideal gas, you have a real gas. We talk about this in thermodynamics. But you have a real gas, then this formula is not applicable. This formula applicable only in the ideal gas. But if you have a real gas, so real gas you can use many other equations. This is one of them. Van der Waals equation of state for non-ideal gases. There you have to know the A and B, and it's more complicated. Okay, so that's how you can use. And again, this is a correlation. Okay, this is a correlation. Fitting of data here. Other equation that you can use. This is also from thermodynamics. If you want to know pressure at different temperatures. Okay, for example, I want to know pressure in the vapor phase, and I know the another pressure at another temperature, so I can calculate the other pressure from another temperature. Okay, this is known as Clapeyron equation. It works on the when the system is in equilibrium, when the vapor and liquid phases are in equilibrium. Only then you can apply this equation, and you will see this in thermo. Okay, just an example here. How to get pressure because pressure is a physical property. So how to get pressure if you know the pressure at some other point, and this is known as heat of vaporization. Heat of how much heat required. This heat of vaporization means how much heat required to convert liquid into vapor without without changing the temperature of the system. Well, I will explain you this in thermo. No need to explain it here. Okay. Another law that we use is a Raoult's law. Now here, Raoult's law is used again at in equilibrium when we say that the vapor pressure. Now, yeah, one more. Sorry, I forgot about. So far, I only told you about one phase. Okay, one component. Sorry, one component. Only this is only for one component. What if you have a mixture of components? Like, for example, you have water and let's say methanol, or you have toluene and benzene. You have a mixture. When you have a mixture, you apply Raoult's law. Okay, Raoult's law comes into place when you have a mixture, and we always have a mixture. As you know, crude oil is a mixture of thousands of hydrocarbons. While you are making ammonia, ammonia is a mixture. Ammonia is made from the mixture of nitrogen and hydrogen. So most of the time you will deal with the mixtures, right? Because you are converting raw material to the product. So you always have a mixture in the industry. You will rare you will have a single compound. So when you want to know the equilibrium for mixture, we apply the Raoult's law. The Raoult's law says that the vapor pressure of the component I, any component I, is proportional to its concentration in the liquid phase. Okay, so this is the Raoult's law. So if you want to know the pressure of a component in the gas phase, you calculate, you measure the concentration in the liquid phase and put this vapor pressure. This vapor pressure you calculate from Antoine equation. This one from Antoine equation above the equation I showed you. From there, you calculate the pressure and you measure the concentration from the sample, and then you can calculate the pressure of component I, Pi. Why we need the Raoult's law? Raoult's law we need to design the flash drum here up uh, here. If you look at this here, this flash drum, because flash drum this is a mixture of ammonia and nitrogen and hydrogen, and here the vapor is going up and the liquid is coming down. But this is a mixture. This is not a pure compound. So there you need to know the vapor pressure and the real pressure of the component I. So if you want to know the pressure of any component I, like component nitrogen or component hydrogen or component ammonia, then you have to use the Raoult's law, because Raoult's law is used for mixtures. Okay, for mixtures. So don't worry about this equation. This is the equation of Raoult's law. Similarly, sometimes you need to measure the enthalpy, because this is very important when you are designing furnaces, right? How much temperature you want to increase. So you need to how much heat you supply, how much fuel you want to burn. This dH is the enthalpy of the system, right? What is enthalpy? I told you yesterday, most of you were there in thermo. Enthalpy is the amount of energy contained by the fuel, right? So if I want to increase the temperature of my component, like for example here, look here, if I go back here, here they are at the room temperature, but I need to increase the temperature of nitrogen and hydrogen in a furnace, right? This furnace, here, this furnace here. I want to increase the temperature of nitrogen and hydrogen to 400 degree for the reaction. So that how much heat I need, how much heat I need in the reactor, or in the heat exchanger, right? So if I go down, this equation will tell you. Uh, this equation. This equation will tell you how much fuel you want to burn to increase the temperature of nitrogen, hydrogen, ammonia to 400 degrees centigrade. And then you have to buy the amount of the fuel. You have to pay money for that fuel. You see my point? And so this is the equation. This is also a part of thermodynamics, because whenever we talk about heat and we talk about pressure, temperature, volume, and work, this all the area of thermodynamics. Okay. So there are this we write, we integrate this equation. This is a differential equation. As you can see, this is a derivative. If I write the derivative, dH over dt, here, sorry, temperature, this will go away. I put the dt over other side. So this is a differential, right? Derivative. Derivative of H with respect to temperature. That is Cp. So we integrate. I got delta H going from temperature 1, which is the room temperature, to 400 degree in case of ammonia. So how much heat I need in the heat exchanger? This is like designing a heat exchanger. This is a heat exchanger design equation. Okay, and Cp depend upon the temperature. And how I find Cp? Cp you find by this relation A, B, C, D, whatever. So this again, here the data involved is how to get data for Cp. As you can see, it's very important how to get Cp data. So CP data you can read from the handbook. If not there, you can do the experiment. If you cannot do experiment, then you have to use the equations. Equations, okay. Similarly, as I just told you, density is the reciprocal of volume, so P is equal to rho RT. And then also comes the calculation of mixture properties. Okay, this is the example. How to calculate the density of a mixture of water and methanol. Here, let me highlight this one. Here, how to calculate the density of the mixture of water and methanol. With methanol is 40% by weight, it means the gram, and the density of water is this kilogram, I think, yeah, kilogram per meter cube, and the density of methanol is 79.2 kilogram per meter cube. So we would like to know the density of the mixture, not we are giving the density of water, pure water and pure methanol. We want to calculate the density of the mixture. Okay. So how we proceed? Because we have to use the equation. Like you can go through this one. This is very easy. We can take the basis 1000 kilogram of the mixture. It means that 400 kilogram of methanol here, because methanol is 40%. So it has to be 400 kilogram of methanol and 600 kilogram of water, right? And we know this is a formula: density of the mixture, total mass of the mixture divided by total volume of the mixture. So total mass we already know, 1000 kilogram. We want to know the total volume. So how we get the total volume? We get the total volume by the individual volume, right? So total volume will be the volume of water plus volume of methanol. So how do I calculate volume of water? Volume of water is mass of water over density of water. So mass of water is 600, density is given, and similarly volume of methanol 400 over this density, and you sum them together. Well, so you will get the total volume. You put the total volume here, and you will get the density of the mixture. And this how you got the property density by simply using the formula. Density is equal to mass upon volume. This is more simple. Density is equal to mass over volume. Sorry, volume. Okay. By this simple equation, I calculated the mixture. I tell you one more thing here. In the handbook, you will not find properties of the mixture. You only find properties of the pure compound. 99% pure compound. If you are dealing with a mixture, then you have to do the calculations by using simple equations. Okay, keep this in mind. For example, you want to calculate the temperature. This is known as a as a critical pressure. Sorry, critical temperature, critical pressure. We will talk about this in thermodynamics as well. So if I want to find the temperature of the mixture, okay, temperature of the mixture, then I just have to take the average value. So for example, suppose in this example, uh, let's see, we have temperature 50% is one compound, okay, 50% another compound, and the temperature of this compound is 304, and the temperature of another compound is 369.8. So what should be the temperature of the mixture? I just multiply by the mass fraction into the temperature of that compound. So the mass fraction of first compound into the temperature of the first compound plus mass fraction of the second compound into the temperature of the second compound. So that's how I get the temperature of the mixture. This is temperature of the mixture. Let me write it here for you. Give me an example. Uh,
And this is accurate or estimated, doctor?
we estimate for the mixture as I told you. We estimate. We do not have available mixture from the handbook or from other sources, right? This has to be accurate. The temperature of the component compound here. For example, let's say I have like nitrogen. We have nitrogen. Let's say 50% by weight. Why doesn't come? 50% by weight. Okay, and the temperature is, let's say, 250 degree Kelvin. And we have hydrogen, also 50% by weight. Okay, and the temperature is 320 Kelvin. Okay, Kelvin. We mix them together. Okay, so what should be the temperature of the mixture? Mixture. Okay, so here we can calculate. Simply put, the temperature of the mixture is equal to the mass fraction of nitrogen multiplied by the temperature of nitrogen plus mass fraction of hydrogen multiplied by the temperature of hydrogen. Okay. That's how you get the temperature of the mixture. Like this should be 125, I guess, 125 plus and 320. So
160.
160. Yeah. So we get the temperature of the 285.
85, yeah.
Okay. This is how you can do. This is not ideal, but this is basic simple calculations. Okay. Some properties you cannot add like this, but temperature, pressure, this I will tell you later. Or it's called eccentric factor. This is used in thermodynamics. Okay. And that's how you calculate the data for the mixture. Now the last topic, and I will finish. Maybe we leave early today because I went very fast because the video is recording here, so you can go through. Another thing, when you are designing, I don't know. Last semester, people don't understand. Thousand times I told them that we are designing the primary, or maybe very basic designing. Okay, very basic designing, very basic design, not details. So when you are doing the basic, you use rule of thumb. Rule of thumb. To get quick estimates, we use the rule of thumb. Now, what is the rule of thumb is? Rule of thumb is that you develop some data based on your experience. Okay, it's called, yeah. I mean, there is no, you don't look in the handbook, you don't use any equation, you don't do any calculation, you just guess. This is known as a guess based on one's experience. This is called a guess. For example, if you are in auto industry and you are working for different, you are looking for, somebody comes to you and asks you, okay, can you please tell me what will be the price of a Toyota Camry model 2015? If you are in the industry, you will give him a guess based on your experience. Rule of thumb. That is known as a rule of thumb in engineering analysis, because sometimes it is very difficult to calculate. So people do guessing there, and you will see when you design the heat exchanger and other equipment, you will see those are known as rule of thumb. Like for example, if you want to increase the pressure, right? If you want to increase the pressure of a gas, so there are three options you can use. Either you can use the fan, you can use the blower, or you can use the compressor. You know, the compressor gives very high pressure. Lower, if you want not very high pressure, you can use the blower, and below the blower are the fans. Okay, so what I am going to use, so it says the one of the rule of thumb is fans are used when the pressure is about 3%, increase in 3%. For example, if you go from 1 bar to 1.03 bar, it says that if you want to increase, one of the rule of thumb based on the experience, if you want to go from 1 bar to 1.03 bar, use fan. You are getting my point or no?
Yes, yes.
Yes, yes, teacher.
Okay. Similarly, reciprocating pump decrease the pressure to 1 torque. These are all the values there. These are developed by the operators. working there, many years of experience. Now chemical industry, we have like about 100 years of experience. So why am I wasting time doing the calculation? I just can do some rough estimation. Okay. So these values are efficiencies of fan vary from 60 to 80%. For example, you are designing a fan. Okay. In fan, there is a factor called what is the efficiency? How much efficiency can I use? Sometimes the answer is not available. So what you go? You go to the rule of thumb. That okay, I can use between 60 to 80%. Okay. So any value you can take the average value 70% and you can put. Because why? Because you are not doing the detailed designing. You are doing the basic designing. Just for estimation. Only for estimation. Only for estimation. Here. Similarly, there are many rule of thumb here. You can read by yourself. If you understand what I am telling you now, these are just the values. You don't have to remember. Just I give you. I will send you one textbook. I will upload one book. It's known as the rule of thumb for chemical engineers. Rule of thumb for chemical engineers. You can type in the Google. You can download the book. Maybe I can show you 1 minute.
Teacher,
Let
just a
me.
minute.
Yes.
For the first one, the third line, the rotary piston,
Here. This one compressor and pump.
the rotary piston is from 0.001 to 0.001. There's no difference between the two numbers.
Maybe zero. Yeah. Maybe typing mistake. Maybe 0.01 torr. I just copied from the. I will show you the rule of thumb. 1 minute. Just a minute. Let me stop this and share with you. uh, share, share. Home tab, new tab. If I go here and I type rule of thumb for chemical engineers, this is a book. This is a book, but this is not. Yeah, rule of thumb for chemical engineers. So even if I tell you this concept, if the concept is not clear, you can go here always and you can. I have a copy of this book. Okay, I have a copy of this book and I will inshallah upload it. So you can take a look at the book. Okay, why it doesn't go down? Maybe some problem. Anyway, okay now.
Yes,
So
teacher.
the book provides all the rule of thumb for designing, or
Yeah. All the rule of thumb you can go and study. We will not be using. I will give you the rule of thumb for that equipment, but just for you to understand. The students are confused because they think everything has to be calculated by the formulas and from the graph. But sometimes experience also matters. You don't have to waste your time looking in the handbooks and calculating the formulas. So just give the values.
no?
Anyway, this is not working, so I will close this one.